Alright, we're going to go back over how to determine the polarity of molecules. By request, test is tomorrow. We're going over this. This is what we're reviewing. Alright? Let's take this opportunity to remind you about what polar molecules are. They have an uneven electron density. And this uneven electron density creates a molecular dipole. Density, electron density. A molecular dipole is also called a polar molecule. Because there is a partial positive and a partial negative This is the symbol for partial positive, the symbol for partial negative. It's like an 8 you don't quite finish, or an S that you kind of loop at the bottom. You need to know that's what it means. I'm not sure if it's required that you label it that way on the test, but you need to know what that symbol means. Yeah, I'm sure it would help you too if I gave you a copy of the test before the test, but I'm not going to do it. You can always ask me. Well, let's finish this right now, okay? All right. So, to figure out whether you have this uneven electron density, to figure out whether you have polarity, you need to understand about electronegativity. Okay? And electronegativity is a comparison of how hard one atom pulls on the electrons it shares with another atom. Okay? And if there's sharing going on, that means it's a covalent bond. Alright? So to figure out, yep, how hard one atom pulls on the electrons it shares with another atom. To figure out if a molecule is polar, to figure out if it has a dipole, you must figure out if there is asymmetry. Asymmetry means not symmetrical. Asymmetry among polar bonds. So right away, you should be able to tell from this definition is if you don't have polar bonds, you can't have a polar molecule. Okay? If you don't have polar bonds, you can't have a polar molecule. If you have polar bonds, then you need to figure out if those polar bonds are asymmetrical. Okay? So that's what it takes. If the polar bonds are asymmetrical in some way, then you can have a polar molecule. You got to put your name on there, right? Use that if you want to. So let's use this molecule here. It might exist. I don't know if it actually does or not. I could have used F2. I know it exists, but that's all right. We'll use this one. In Unit 3, we learned to figure out the shape of a molecule like this. Okay? And we started with electron dot notation. Hydrogens, we know, have only one electron in the valence level. I've got 2 hydrogens. We know that carbons have 4 valence electrons. And we know that chlorines, or if you don't know it, you should be able to figure it out from the periodic table, chlorines have 7 valence electrons. And then there's something called the Octet Rule, which says that most atoms want to have a valence electrons. Okay? Essentially what they want to do is to have the same electron structure as the next highest noble gas. For hydrogen, the next highest noble gas only has 2 electrons. The next highest noble gas is helium. So by sharing just this electron with a carbon, that gives hydrogen the same electron configuration as helium, roughly. Okay? And so that makes hydrogen more stable. Carbon, on the other hand, its next highest noble gas is neon, and so it wants to have 8 electrons like neon. So I can share these 2 electrons and these 2 electrons, and that gives the carbon, it went from 4 to 8 electrons. It has 8 electrons now. And each of the chlorines, which had 7 to start with, by sharing one with carbon, now have 8. So they're like argon. Chlorine's next highest noble gas is argon. From that, then we want to draw the Lewis dot formula, where you squeeze the electrons in between the atom symbols. So here's a hydrogen, and there's 2 electrons shared between hydrogen and carbon. So I'll put it there like that. And these 2 are shared between this hydrogen and carbon. Put them like that. These 2 electrons are shared between a carbon and a chlorine. And I have to keep those lone pairs that remain. And there's your Lewis dot formula. That's called a Lewis dot formula. Alright, once you have a Lewis dot formula, you need to determine how many electrons there are that are called sets around your atom of interest. Well, most of the time in high school chemistry, the atom of interest is going to be the central atom. Okay? So carbon's the central atom, that's our atom of interest. Sets can be lone pairs. Well, there are no lone pairs around this carbon. Sets can also be all the electrons shared between 2 atoms. And so there's a set shared between these 2 atoms, and a set shared between these 2, a set shared between these 2, and a set shared between these 2. So that's 4 sets of electrons. Anytime you have 4 sets of electrons around your central atom, you're going to come up with a tetrahedral arrangement. And this arrangement, the first arrangement we do, is called an electron pair shape, where we put just the electron pairs around the central atom. Once you have an electron pair shape, then you go back and look at your Lewis dot formula, and any electron pairs that are shared. In the next drawing, we're going to replace those shared electrons. So instead of a pair of electrons up here, let's say we're sharing this one for chlorine, I'll put chlorine here. Instead of the electron pair down here I had, I'm going to replace that with the hydrogen. This one over here is coming out towards you. I'm going to replace that pair with a hydrogen for this one. And this last pair back here that's swung back behind things, that's what the dotted line means, it's swinging back behind, we're going to replace with a chlorine. Okay? So at this point, we've gotten rid of all the electron pairs. So we now have the molecular shape. To remind you, this is a tetrahedral. This is also a tetrahedral. It's the same geometry, but the type of drawing is different. This is called an electron pair shape, and once you get rid of all the electron pairs, you've got a molecular shape. So this is a tetrahedral molecular shape. Well, if you only had 3 here, 3 sets of electrons, that would be a trigonal planar. And you wouldn't have these arms that swing toward you and away. You'd have it just straight out. It's 120 degrees all the way around. Okay? All right. So, now, all of these bonds are equally spaced. So, the molecule could be considered symmetrical. Okay? But we don't care so much about the molecule's symmetry. We care about the polar symmetry. Okay? It's the polarity of bonds and that symmetry that will tell us whether they're a polar molecule. So we got to look at what the electronegativity difference is to figure out whether these bonds are polar or not. So let's do first the electronegativity difference for the carbon to chlorine bond. So the electronegativity for chlorine, and you find that on your periodic table in your test references that list the electronegativity. Yep. Chlorine's electronegativity is 3.16. The electronegativity for carbon, 2.55. What? It's on the periodic table with electronegativity. It's right up under the list of common ions. Oops. Alright, so the difference then, the electronegativity difference for a carbon to chlorine bond is 0.61. Polar bonds have an electronegativity difference greater than 0.5. So the carbon to chlorine bond is polar. Alright? Now this only works when you're talking about covalent bonds. And this is covalent bonded, we know, because everything is nonmetals. Okay? So but combining a metal and a nonmetal, we wouldn't even worry about this. You got a question?
How can we then protect the electronegativity of hydrogen?
We're going to do that next. We have to do that too. We have 2 different kinds of bonds. we have a carbon to chlorine bond, but we also have a carbon to hydrogen bond. So we got to look at both of those for this molecule. Yeah, you could do it all together, but it's probably, in this class I've taught you to do it separate. Okay, so we can look at the polarity of the individual bonds. Okay? Yeah. It says polar bonds have an electronegativity difference that's greater than 0.5. I didn't say that this was 0.5, I said it's greater than 0.5. Alright? So now let's look at that other bond. Electronegativity for carbon, we said, was 2.55. And the electronegativity for hydrogen is 2.1. So we subtract that, and we get 0.45. But what I taught you in Unit 1 was anytime you got an empty slot, you have to round off that digit. So the answer we actually want is 0.5. So the electronegativity difference for a carbon to hydrogen bond is 0.5. Since polar bonds have to have an E and D, electronegativity difference that's greater than 0.5, then in this class, we consider this to be nonpolar. And I say in this class with emphasis because it really depends on what textbook, what teacher, what professor. I'm trying to keep it as simple as I can. And technically, really, polarity gets way more complex than we teach it in here. We're just trying to start with the very beginnings of it to kind of get an understanding, a general understanding of it.
So that's the only time you get it in the that's the only time?
The only time you round it off? Yeah, the way I taught you to do rounding off for addition and subtraction is that anytime you have an empty slot to the right, you underline those digits that result and then round those off. And you use this notation to do it. Yes. Does that answer? No, because there's no empty slots over here. Okay? Alright. So since polar bonds have to have an electronegativity difference greater than 0.5, we're going to call this a nonpolar bond. Okay? You know, by some measurements, this would be a polar bond, but we're going, and either way, you're going to come up with the same molecule. Alright, you'll come up with the same polarity or not. Okay? So we need to look now at the molecule and see what the result is of these polar and nonpolar bonds. So this is where we use those dipole moment arrows. So we'll redraw this same drawing, but instead of just showing the bond, I want to show the bond with the direction of electronegativity. And we're going to point the arrow toward the element that has the greater electronegativity. So this bond is polar. The greater electronegativity lies with the chlorine. So instead of just a bond arrow, I want to have an arrow that shows the polarity. The more positive end is down here, the more negative end is pointed toward the chlorine. The other chlorine is going back behind, so I'll do that with a dotted line. Put an arrowhead on the end, cross the hatch here, and put the chlorine back here. Now, we consider these hydrogen bonds to be nonpolar, so we're not going to put any arrows on this. All right, think about it a little bit. Do we have an asymmetry, an unevenness in the way that the polar bonds are arranged? Well, these are not polar. These are polar. Is it uneven the way they're arranged? Yeah. If I had these same bonds all the way around, if this were carbon tetrachloride, instead of having hydrogens down here, have more chlorines, you'd have arrows all the way around, going opposite from each other. So that'd be a nonpolar molecule. This is polar because the arrows are arranged in an uneven manner.
So it has to be uneven to be polar?
For it to be polar, you have to have an asymmetry among polar bonds. These are the only two polar bonds. Okay? They're asymmetrical. They're not evenly arranged. Okay? So this is going to be a polar molecule.
So you draw one,
I'll be glad to. Sure, sure. I'll be glad to. I'll show you two more, in fact, okay? Just to be clear, as clear as I can. Maybe more than that. That's not molecular, polar molecule. What now? The chlorine is more electronegative than the carbon. First of all, you don't draw arrows if it's not polar. So we didn't draw arrows here because we consider that to be nonpolar. We drew an arrow here because this is a polar bond, and we draw it toward the element with the greater electronegativity. Yep.
So it's polar, it has no arrows, but it's nonpolar, it has
You got it the opposite. If it's polar, you have arrows. If it's nonpolar, you don't.
Okay.
All right? All right, so because I have the polarity that's going in this direction, where the electrons are being pulled more strongly toward the chlorine here and more strongly toward the chlorine here, the combination of all that means that our dipole moment for the whole molecule goes in that direction. So the molecular dipole lies in that direction. This is a dipole moment for the whole molecule. These arrows on the bonds are the dipole moment for the bonds.
Okay, so that right there, you put the dipole moment for the whole molecule in between.
Yeah.
Okay.
You can think about it that way. That's a good way to think about it. That's the way I think about it, actually. Okay? And now, if the dipole moment lies over here, in this direction, what that means is, by definition, up here, the chlorines are pulling on the electrons more strongly than the carbon is. So the electrons are spending more time over here. That means, if they're spending more time over here, the electron density is greater over here and here, and less dense over here. Okay? So that means if you got more electrons over on this side, this end of the molecule is partially negative. And if they're more often over here, then this end of the molecule, it's kind of like you've sort of uncovered the protons in the nucleus a little bit. So this end of the molecule is partially positive, where all the hydrogen is located. Does that make sense?
So wherever the dipole moment is negative on the opposite side.
Say that again.
What the arrow is the dipole moment?
This is the dipole moment arrow. Shows the dipole moment for the molecule is in this direction.
Okay, so that side is negative.
This side is negative, and that's what this symbol right here means, partially negative. Okay? Now, let's use this same carbon arrangement, but change around some of these other elements around here to look at what happens. Okay? Just as an example, let's take and put carbon and put 4 chlorines on this thing. Alright? I'm putting 4 chlorines around carbon. This would be carbon tetrachloride. Okay? We didn't change the polarity of the bond. This bond is polar, right? Okay, so all the arrows are pointing out toward the chlorines on this. So in this example, all the bonds are polar, but they're evenly distributed. In order for it to be polar, you have to have asymmetry. But this is symmetry for polarity. It's nonpolar. Okay? Let's replace all the carbons, these 2 chlorines with a hydrogen.
You wouldn't draw a dipole moment for a molecule?
No, because it's nonpolar. The molecule's not polar. You only draw a dipole moment for the molecule when the molecule's polar. The bonds are polar, but the molecule's not. So there's no dipole moment. No dipole moment. Okay? So let's look at what happens when we replace the 2 chlorines we had up here with hydrogens. Sure. All right. In this case, the hydrogen to carbon bond is nonpolar, right? And in order to have a polar molecule, you have to have polar bonds. Since there's no polar bonds, this is a non-polar molecule too. But for a different reason. Well, actually it's the same reason, but it's got an extra reason for being non-polar here. Okay? Non-polar bonds all the way around. Okay? That means that must be a non-polar molecule. That help you out? And of course you can have molecules that are bent and trigonal pyramidal. I would have to calculate the E and D here. Let's just look at this for a minute. All right, here's a molecule. It's ammonia. Without doing the calculations on paper, I showed you how to do calculations for electronegativity on this. I'm just going to give you the electronegativity here, or electronegativity difference with this one. Nitrogen's 3.04, hydrogen's 2.1. So we're going to have a 0.9 electronegativity difference. The electronegativity difference here for a nitrogen to hydrogen bond is 0.9. So that's polar bonds. Okay? Those are polar bonds. Nitrogen is more electronegative. All the arrows are pointing in that direction. Okay? What? So I can show you, well, because nitrogen is more electronegative than hydrogen, and the electronegativity difference is greater than 0.5. Okay? This is an uneven arrangement. Okay? So by definition then we said, since all the bonds are the same and they're all polar, that unevenness creates an asymmetry. That makes this a polar molecule. Does that make sense? Yeah, there is I haven't drawn it, but there is a dipole moment. Since we have, it's like, you can think about this like the top of the hill, and everything's going toward it, right? Overall, then, the dipole moment for this goes in this direction. Well, if the arrows were pointing down, it would. If the arrows were going in this direction instead of up, it would go down, yeah. So, let's say I replaced, well, that wouldn't give me polarity. Let's see what would give me polarity. If I replaced all the, that wouldn't give, yeah, it would. If I replaced all the hydrogens with fluorines, fluorines are more electronegative than nitrogen, so that would turn the arrows around, and the dipole moment for the molecule would go in the other direction. All right? Yes? Because the nitrogen is more electronegative. See, up here we calculated the electronegativity for this bond to be 0.6, but the arrows point toward chlorine because it's more electronegative than carbon is. The arrows point toward the more electronegative element, but you only write arrows when the bond is polar. Does that make sense? And then you look and see, is it an uneven arrangement? Okay? Now the little tip I gave you, sometimes we call it a trick, but it's a tip that helps you. If when you're drawing out these shapes here, okay, you're finding the shape of the molecule. If you have a modified electron pair shape with at least one lone pair of electrons, when you have to remove those to make the molecular shape, you will have asymmetry for the molecule. So if the molecule is asymmetrical, all the bonds are the same and they're all polar, you're going to have a polar molecule. That makes sense? Any other questions about that?